Linear Algebra, Chapter 1. This is where we begin the basic vocabulary behind what we are going to be doing all semester. We'll start looking at how to set up linear systems in matrix form and how to solve them, and some of the basic ideas behind matrices. I'll try to start each chapter with a vocabulary list, so you see what you need to study and be ready for on the quizzes and the exams. These are some of the proofs that we were introduced to. The idea of component proofs. For example, if you want to prove that the elements of a matrix have zeros in them, then you want to use a component proof. We talked about proof by induction, which is basically to prove something like the nth case. For example, we had something like A transpose to the nth power turned out to be A to the nth transpose. So anytime you're looking at an nth power, that would be a good example of when to do a proof by induction. Proof by contradiction, this is best used when you're trying to prove something exists or it is unique. And so you prove the opposite, which is to prove that it doesn't exist or it is not unique, and consequently you arrive at a contradiction to the original given. And then a general proof is just when you use properties and definitions to put it together. So that is the most common kind of proof that we will be talking about. So to begin, let me start with some applications. We talked about how to find the equation of a circle if it goes through 3 points, and I mentioned in class that it is a unique circle that has to go through each point. So first you want to come up with an equation that represents the circle. And the classic equation for a circle would be something like x squared plus y squared plus ax plus by plus a constant equals 0. So you're using each of these points, negative 2, 0, 5, 7, and 1, 8. Substituting in the coordinates for x and y, I can come up with an equation involving 3 variables, a, b, and c. So substituting in the point negative 2, 0, I get the equation 4 plus 0 minus 2a plus 0b plus c equals 0. Substituting in 5, 7, 25 plus 49 plus 5a plus 7b plus c equals 0. And then substituting in the point 1, 8, 1 plus 64 plus x plus 8y plus c equals 0. So if I write this with the constant on the right-hand side, I'm going to have the following equations. Negative 2a plus c equals negative 4. 5a plus 7b equals negative 74. And x, this should be a and b. So the last equation is going to be a plus 8b plus c equals negative 65. And it looks like I'm missing a c in the middle equation. So basically, if I set this up in matrix form, it'll look like the following. Using a matrix to represent my coefficients, I'll have negative 2, 0, 1. I will have 5, 7, 1, and 1, 8, 1 times the vector a, b, c equals my constants, negative 4, negative 7, 4, and negative 65. Now we're going to set this up as an augmented matrix instead that I can use row operations to reduce. So my augmented matrix will look like the following. Negative 2, 0, 1, 5, 7, 1, and 1, 8, 1. And on the augmented side, negative 4, negative 74, negative 65. From there, I would use row operations such as swapping 2 rows, multiplying a row by a scalar, adding a scalar multiple of one row to the other to get it down to reduced echelon form. Or actually, I can use my calculator to get it to row reduced echelon form. And row reduced echelon form would look like the following. 1, 0, 0, 0, 1, 0, 0, 0, 1. And then on the other side, I would have negative 19 over 5 and negative 31 over 5, I believe, and negative 58 over 5. So what this means is that A equals negative 19 over 5, B and C consequently. So my final equation for the circle would be x squared plus y squared minus 19 fifths x minus 31 fifths y minus 58 over 5 equals 0. Or if you prefer, we can multiply everything by 5 and get a more standard equation for a circle. 5x squared plus 5y squared minus 19x minus 31y minus 58 equals 0. So I want to go back a couple of pages and just to kind of review the difference between REF and RREF. So in row reduced echelon form, basically this is when you can actually solve the system because you can read off either individually or parametrically what the solutions are. So row reduced echelon form has leading ones, and above to the left and below the leading ones are zeros. So you're going to get something like 1, 0, 0, 7, augmented 5, 0, 1, 0, 5, 6, and then something like 0, 0, 1, 3, 9. So leading ones are here, here, and here. And notice to the left, below, and above the leading ones are zeros. And so we can actually read our solution off of this. It would be something like x1 equals 5 minus 7x4. x2 equals 6 minus 5 x sub 4. And x sub 3 equals 9 minus 3 x sub 4. As opposed to a row echelon form, which is pretty much just an upper triangular kind of a form. So in this one, we have zeros to the left and below the leading ones, but not necessarily inside. So you would have something like 1, 2, 3, 7, augmented 5, 0, 1, 0, 6, 4, and then any rows of zeros are automatically put on the bottom. So in REF form, you still need to solve, but it's easier to solve and you use what's called back substitution. So that's a quick review of the difference between REF and RREF. For the majority of the time, since I am solving, I will use REF to solve it together. So here's another example of how we could set up a matrix to solve a particular situation. I have a matrix times a vector, and I want the result to equal negative 4 times the vector. So before I start working with the numbers, I'm going to work with the equations here. So here basically, I have AX plus 4x equals 0. If I factor out the x, I have a plus 4, but it has to be a matrix, so this is going to be 4i times x equals 0. Now this is what's called a homogeneous system. A homogeneous system is when you have a linear system equal to 0 that you're solving. So rather than solving ax equals negative 4x, I'm going to solve the homogeneous system a plus 4i x equals 0. And a plus 4i is the matrix 1, 6, 5, 2 plus 4 times the identity matrix 4, 0, 0, 4, and x equals 0. So if I put this in augmented form, I'm going to have 5, 6, 5, 6, augmented 0, 0. So using row operations, basically I'm going to do row 2 minus row 1, and I'm going to get 5, 6, 0, 0, 0, 0. So the solution to this is going to be an infinite number of solutions. Basically, the solutions have to satisfy the equation 5x1 plus 6x2 equals 0, or x1 equals negative 6 fifths x2. So if I were to write this in vector form, I would have x1, x2 would equal negative 6 fifths x2 and x2. And pulling out the x sub 2, basically any multiple of negative 6 fifths and 1 is a solution to this homogeneous system. Okay, so now let's talk about how to analyze a matrix for different situations that would generate different types of solutions. So I have a linear system here, and the first thing I'm going to do is rewrite it as an augmented system. So my augmented system for this would be 1, 5, 0, 2, 0, 2, 1, 9, 0, 16, M, and P. And basically what I'm going to do is row operations until I get this down to RAF, and then it's a little bit easier to analyze what the possible cases would be for each solution. So I'm going to take row 2 minus 8, row 3 minus 8 row 2. Since row 1 and row 2 are already in that upper triangular form, now I need to just get row 3 in that same kind of a situation. So if I do that, I have 1, 5, 0, 2. 0, 2, 1, 9, and 0, 0, M minus 8, and P minus 72. Now, typically you would divide row 2 by 2 and row 3 by M minus 8, but even at this point we can talk about possible situations. And what I want to focus on is that last row. So, in, let's say, case 1. So, case 1, let's say I have M minus 8 equals 0, and P minus 72 equals 0. Well, if that were the case, then my matrix would be 1, 5, 0, 2, 0, 2, 1, 9, 0, 0, 0, 0. So if I were to set up the equations that this came from, it would be x1 plus 5x2 equals 2. 2x1 plus x3 equals 9. But notice I don't have a third equation, which means this is going to end up with infinite solutions. If I were to solve this, it would be something like x1 equals 9 minus x3 over 2. And then if I solve for x2, it would be 2 minus x1 over 5. But x1 I can resubstitute with 9 minus x sub 3 over 2 all over 5. So this would generate an infinite number of solutions based on the parameter x3. So infinite solutions are basically when you have this 0, 0 kind of a situation. And infinite solutions if m equals 8 and p equals 72. So there's my first case. Okay, second case. Let's say second case. I have m minus 8 equals 0, and p minus 72 is not equal to 0. So then I have, if I rewrite it, something like 1, 5, 0, 2, 0, 2, 1, 9, 0, 0, 0, and some number that's not equal to 0. But if I were to take that last equation and reinterpret it, what I have is I have 0x1 plus 0x2 plus 0x3 equal to some number that's non-zero. And since that's not possible, this is a situation when we would have no solution. So no solution if m equals 8 and p is not equal to 72. Now let's take a look at our last possibility. So our last possibility would be m minus 8 is not equal to 0. So again, the upper triangular form would be 1, 5, 0, 2, 0, 2, 1, 9, 0, 0, some number, and then I have over here p minus 72. But let's solve this k right here. If I were to solve that, that means that kx3 equals p minus 72, and x3 equals p minus 72 over k. Now, typically I have to worry about k equaling 0, but in this case, I already said it's not equal to 0. And that means I can solve for x3, which means going back here I can solve for x2, which means back here I can go ahead and solve for x1, which means I have a one solution situation if m is not equal to 8. Now notice I don't need to consider p minus 72 equals 0, because if I have in my bottom row something like 0, 0, 0, 3, 0, all that means is that x3 equals 0, and then I would go back and solve for x2, which would be 0, and x1 would also equal 0, and if you call, that's our trivial solution. Now that's not the only solution possible, that's just from this example that I made up. Let's talk about multiplicative inverses. And actually, to make life a little bit easier, I'm going to take one that's a little bit easier to work with, but you're going to get the same idea. So I'm going to use a 2 by 2 matrix. 2, 2, 1, 3. Now, let's review the way that you found inverses before my class. So 2, 2, 1, 3, its inverse is 1 over the determinant times, and you flip the 3 and the 2, and use the opposite of the upper right and the lower left. And the determinant is 1 over AD minus BC. So in this case, 1 over 6 minus 2. And then 3, negative 2, negative 1, 2. Now, that technique only works with a 2 by 2 matrix, so I'm going to talk about the other way we learned in class, how to find the inverse, and you'll see how they correspond to each other. So the other way I talked about finding an inverse in class was you write your matrix 2, 2, 1, 3, and augmented next to it, you put the identity matrix. And then you do row operations on the left side until it looks like the identity matrix. And as you're doing row operations to change the left side to the identity, the right-hand side becomes your inverse matrix. Now, as I'm doing this particular one, I'm going to define the elementary matrices that are used to define the inverse. The elementary matrices basically represent a single row operation. So the first row operation I'm going to do is I'm going to swap row 1 and row 2. So I'm going to call elementary matrix number 1. A swap between row 1 and row 2, which would look like this. 1, 0, 1, 1, 0. So if I apply that to this, I'm going to have 1, 3, 0, 1, 2, 2, and 1, 0. And basically what's happening is I'm taking my matrix A and I'm multiplying it by E1 when I do that. Now I'm going to do row 2 minus twice row 1. So I'm going to call that E2. E2, row 1 stays the same. Row 2 becomes row 2 minus twice row 1. So it's going to look like that. And so now if I apply this to both sides, row 1 stays the same. Row 2 minus twice row 1 is going to be 2 minus 2. 2 minus 6, which is negative 4. 1 minus 0, which is 1. 0 minus 2, which is negative 2. So now what I've done is I've had E1 and A, and I've multiplied that result by E2. Let's make this row 3 divided by negative 4. So E3, row 2 divided by negative 4. Row 1 stays the same. Row 2 gets divided by negative 4. So 0 and negative 1/4. So now we're going to have row 1 stays the same, 1, 3, 0, 1. 0, 1, 1 divided by negative 4 is negative 1/4, and negative 2 divided by negative 4 is 1/2. So again, this is E3 has been applied to E2, E1, A. Almost there, which is why I wanted to do a 2 by 2. Now I'm going to do, let's do row 1 minus 3 row 2s. So that's going to be E4. E4 is going to be row 1 minus 3 row 2s, and row 2 stays the same. So if I do this, then over here I get 1, 0. 0 plus 3/4 is 3/4. 1 minus 3 halves is negative 1 half. And row 2 stays the same, negative 1/4 and 1 half. So now this becomes my identity matrix, and consequently I've had E4 multiplied by E3, E2, E1, A, and that turned into the identity matrix. And what that means is that E4, E3, E2, E1, this has to be A inverse. So A inverse is E4, E3, E2, E1. But that is exactly what I was doing over here on this side, because I had E1, and then I multiplied that by E2, E3, and E4. So over here, I hopefully have A inverse. So if I look at my original, 3/4, negative 1 half, negative 1/4, 1 half, 3/4, negative 1 half, negative 1/4, and 1 half. It does check out with this up here. And so A inverse is equal to this. Now, that means A inverse can be defined as a set of elementary matrices, but that also means A can be defined as a set of elementary matrices. Because if A inverse equals E4, E3, E2, E1, then A has to equal the inverse of this. E4, E3, E2, E1. And that means that A equals E1 inverse, E2 inverse, E3 inverse, E4 inverse. Which kind of makes sense, because if I read it from right to left, I'm going to undo my last elementary matrix, and then undo the one just before it, just before that, and just before that, and I should end up at the original A. Now I want to do a set of different types of proofs, and hopefully this will get you through. I'll try to do a few proofs with each video review that I do here. So first I'm going to prove that the trace of AB equals the trace of BA, and then follow it up with another proof. Now, traces involve the sum of the diagonal elements, so this is going to be a component proof that I put together. And I'm going to start with my trace of AB. So, trace of AB. And you don't have to write this step, I want to just kind of list it out. So basically I'm taking the first row, first column of AB, plus the second row, second column of AB, plus the third row, third column of AB, and I'm adding them all up. So I'm going to rewrite this as a summation instead. So this would be the summation k equals 1 to n of the kth row, kth column, component of the product AB, and then the summation adds them all up. Now, that itself I can re-represent as another summation, because if I multiply two matrices together, basically what I'm doing is I'm taking this row, let's call that the kth row, I'm taking this column, the kth column, multiplying them together and adding up their corresponding products. So I can rewrite this as another summation, k equals 1 to n, and then inside I'll have another summation. Let's say I equals 1 to n. Now basically I'm moving along row k of A, and I'm moving along the columns. And then for B, I'm moving down the rows, and I'm using column k. So that's how that goes together. Now I want to write out some of these elements so you see my next step. So if I were to write out some of these elements, it would look like the following. Let's start with k equals 1, and then I go along all the i's. So it would be A11, B11, and then I'm moving along the I, so that'll be A12, B21, A13, B31, so on and so forth. And then my next part would be when k equals 2, so that would be A21, B12, A22, B22, A23, B32, da 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 da. Now, since this is summation, I'm going to reorder the summation. So, first of all, the two elements inside I can rewrite because that's just a product of two numbers. So I'm going to rewrite that as I equals 1 to n, B, I, K, AKI. And like I said, I can do that because these two are just representing two different numbers. So it doesn't matter if I multiply 3 times 2 or 2 times 3, it should equal the same thing. But I'm actually going to rewrite the order that I'm multiplying this since I have two summations here. I can rewrite this as I equals 1 to n, k equals 1 to n, bik, ka sub ki. And I'm going to show you why I can do that. So if I rewrite these elements, I'm going to hold I constant. So I equals 1, and we'll go through all the values of k. So that'll be B11, A11, and then B12, A21, B13, A31, da da da. And then I equals 2 would be B21, A12, plus B22, A22, plus B23, A32, plus dot 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 dot. Now let's compare. So A11, B11 is right here. A21, B12 is right here. These two go together. And then A13, B31 would be like the next one down here. A12, B21 is right here. A22, B22 is right here. So I'm adding up the same elements, it's just instead of going sideways, I'm going down. So these two sums are equal to each other. But notice the inside summation, now I can think of that as a sum of two different pieces in a row. That are two different pieces in matrices. I can think of it as row I of column B times column I of matrix J. So this would be B A I. Ooh, let's see. That's an I, right? So this is I. B A I. Getting rid of the K. Make that clearer. So the outside here was I, and this is I. So switch the order of summation. But if I add up the diagonal elements of BA, then that becomes the trace of BA. So notice now, I started with the trace of AB. So I've shown that the trace of AB is equal to the trace of BA. Now, to continue with the second half. The second half was to prove that the trace of A inverse BA equals the trace of B. So, the trace of, what did I say? A inverse BA. Now, since I have this property here, I want to try to use this without having to go into components. I know the trace of AB equals the trace of BA, so I want to set this up as a product of two matrices and then rewrite the order of multiplication. So how about I rewrite this as the trace of A inverse times B times A, since multiplication is associative. So then using my property that I just proved, that would be the same as the trace of A times A inverse B. But then again, because multiplication of matrices is associative, this is the same as trace of A inverse B. But A inverse is equal to the identity matrix, so this is just trace of IB. And identity times B is B, so this is the trace of B. So in this one proof, I've shown a proof by components and a proof by properties. Let's do another property one, just to kind of emphasize, especially with the transpose and the inverse, how the properties work. So I'm going to prove this. So I'm going to start with BA transpose inverse. Okay. Now, first my transpose property. So BA transpose is equal to A transpose, B transpose inverse. But symmetric means that A transpose equals A and B transpose equals B. So in place of this, I'm going to put A, B inverse. And then our inverse property was AB inverse is equal to B inverse A inverse. Now, remember I just assumed that was already invertible, which I gave, so I was okay doing that. So there's a review of symmetric, the transpose, and the inverse properties. We also had something called skew symmetric. And this is a side review. So remember, skew symmetric is when A transpose equals negative A. And one key element of skew symmetric matrices where the diagonals are always 0. Alright, and let's do a proof by contradiction. So proof by contradiction means I'm going to assume the opposite and prove that therefore it is a contradiction. The idea here is basically a proof by contrapositive. So a proof by contrapositive basically how it works is if something is true, then its contrapositive also has to be true. And the contrapositive for this, given this statement here, would be if B is not invertible, which is why I'm going to assume the opposite, then M is not invertible. Okay, so that's basically what we got to do. So let's start this proof. So we're going to say assume M is invertible and B is not invertible. And what I will show is that this is a contradiction, which means M has to be not invertible as well. So we'll start from the beginning. If M is invertible, then you want to think about what it means to be invertible, what kind of properties have to hold. So if M is invertible, there is a matrix C such that Cm equals I. Okay, so that's using the definition of an invertible matrix existing. So if Cm equals I, that means CAB equals I. And that's just using substitution. But if I use the associative property, that means that CA times B equals I. But that means, which means CA must be the inverse. Because the matrix times B equals I, that means that matrix has to be the inverse. And here we go, that's our contradiction. So, contradiction because we assumed B was not invertible. Since the result was the contradiction, that means M can't be invertible. And so, proof by contradiction, by contrapositive, or by contrapositive is done. Alright, so that gives you an idea of the different types of proofs, the component, the properties, and the proof by contradiction, or what I call proof by contrapositive as well. The only one I didn't do is the induction, so take a look at your notes for that one. That one we don't use a lot. Like I said, it's mostly for the nth case, so focus on the 3 that I've shown in this video. Good luck studying. Test is next week. Feel free to come see me this week if you have any questions.